Okay, so um, if you had a question on, I'll tell you before we get there what questions I had planned to go through. If you have a question on one of the other ones, let me know, and then, even if we don't have time to work it out, maybe I can at least give some comments that'll help. Okay. Um, all right. So the first thing I want to define is momentum. And momentum is the letter, the symbol for momentum that people use almost everywhere is P. I have no idea why. Probably because we've used every other letter at this point. And for in Newtonian physics, it is defined to be the mass times the velocity. And since mass is a scalar, but velocity is a vector, that means momentum is a vector. So that means if you have to add momenta, you do it using vector ideas. Okay, so momentum is a vector. And when you just have one object, it's that simple. But as we will discuss, part of the art of using conservation laws is to, they apply for anything. That's why they're so powerful. But it also means that you should choose your system wisely so that you're kind of using them to their full advantage to help you answer whatever question you're trying to answer. So that means that we will sometimes regroup things into collections of objects, and we will just call those things systems. The system will be the collection of objects you're studying or focusing on, in which case you would define the total momentum, which is the sum of all the elements. So you would find the mass and velocity of each thing separately, kind of find the momentum of each thing separately, and then add them up. And so that gives you the total momentum of a system of objects. All right. So that's what momentum is. It's mass times velocity. It's not that complicated of a formula. It's just, you got to know what it is. That's really all there is to it. All right. Then we have impulse. Impulse, the letter for impulse is J. And impulse measures how much interaction the rest of the universe has with your system. So you define a system, the things you care about, and then the rest of the universe maybe pushes on it, pulls on it, does stuff to it. And all those interactions, well, when we're trying to use the impulse and momentum theorem, then impulse encodes how much the rest of the universe acts on the system. And the definition of impulse, the technical definition comes through calculus. And what it is when you have some force acting on a system over some amount of time. Okay, so forces are acting on it or being applied over an amount of time. Technically, what it would be is you would make a graph. I'll draw a picture here. You'd make a graph of force as a function of time. So imagine, you apply no force and you start to apply a force, and maybe it's variable and then it goes down. Okay. The technical definition of impulse would be the area under this curve. So it's kind of like we had kinematics and we had areas under curves and things. In fact, it's very similar to that. For those of you who have had calculus, you'll recognize this as a calculus concept. But okay, that's the technical definition. But it turns out it equals the average force over that time. So what you would basically do is you could imagine that there is, I shouldn't do yellow. It won't show up very well. There we go. Do this one. Do antique yellow. So there would be like an average over this interval. There would kind of be like an average force. I don't know, something like that. And basically the idea is you could replace the true area with the average area, and the area of and you would find that the impulse equals the average force times the interval of time. And this is, so I give you, if you want, this is probably the better way to actually define it. The top one is the most useful for us. Okay. So, all right, they're both true, they're both equal. I'm just going to say, if you're going to use this thing, go to the first one first and go from there. All right, so these are the two quantities we will be focusing on here today. And so impulse needs a force, obviously, and it also needs a time. So the forces are applied over an interval of time, not just, so it takes time for this to happen, this interaction to happen. If you have many different forces acting on your system, then you would want to add them all up to find the total impulse. I didn't write that, but it would be the net or total impulse that would be really important. All right, so those are just definitions of quantities. They may look a little weird, but they're built out of things that we've been playing with all semester. So it's not too hard to use it. If you were to check out the units, it turns out that both impulse and momentum have the same units. Okay. So we're going to build a relationship here in the next, little block here in my notes, relating impulse and momentum. But for them to be related, you have to be able to match up units in some way. And so it just turns out they have the same units. So that's the first kind of check. And it's kilogram meter per second. When you go through the units of impulse, you should use the fact that newtons, so that's a newton times a second, but then you have to unwind newtons in terms of kilogram, meter, and seconds, and you can check that they have the same units. All right, and here we come to the most important thing. That's why it's got the arrow. All right, the impulse momentum theorem. The impulse momentum theorem is as follows. It says that the change in momentum of a system, and it works for any system. So first you define the system. The change in the momentum inside that system equals the total impulse acting on it over some amount of time. It doesn't matter. It works no matter what. So, you could think of it if we had a person in a car. Okay, so you have a person inside a car. You could, and stuff happens. I don't know. There's a cow. In physics, we always talk about spherical cows with horns. Okay, so you could have a cow or something. So the car is going to hit the cow. Stuff's going to happen. Okay, you could try to use the impulse and momentum theorem and apply it to this car. You could do the car by itself. You could do the person by itself. You could do the cow by itself. Or you could regroup it and do the car and person together. Or you could regroup it and do the car, person, and cow all together. You get to choose what the system is. So you make your choice. But whatever you choose, then you would say the total momentum change of stuff inside the system equals the total impulse on the system. And the change in momentum equals the impulse. All right. I wrote it out here for just a system made of one thing, using mass and velocity equals F delta T. So you'd say the change in mass times velocity equals the average force times the change in time. Can you give me a thumbs up if you guys did this in high school? For those of you who took high school physics, is this how you wrote? Do you remember a formula? saying F delta T equals something? Nobody remembers? Okay. Sometimes in high school, people write it as M delta V equals F delta T. Does anybody remember a formula like that from high school? No, somebody, Jessica does. Okay. So in reality, this is not quite true. These two are only equal if mass is constant. So there's a slight jump here. The one above is true no matter what. This one is sort of a special case. Okay. Now you say, when does mass change? Well, we just came out of Thanksgiving. Everybody's momentum changed, their mass changed then. Or there's an example in sapling, and I'm going to do it, work through it, where the mass, there's a train car going down the track, and then, I don't know, stuff is dumped on it as it goes down the track. And so the mass changes. And so you have to account for that. Okay. So this is the version I would use here. Well, one of these two, whatever is most appropriate for you for the situation. Are there questions? That's kind of our key equation, our key formula that we're going to use over and over and over in this assignment. Okay, so how do we do this? I have a little rundown, my I guess list of steps to solving problems using impulse and momentum. So the steps are as follows. I guess step one is read the problem and then figure out what you're trying to solve for. So figure out what quantity you're trying to find. And okay, and the problem may have several different things, and so you may have to go through this process several different times, and that's okay. Okay, once you identify what you're trying to find, what number you're trying to determine, then you want to group the problem, the things in the problem, to define a system, and you want to do that in a way so that basically the only thing that you need to know, or that the thing you're trying to find is the only unknown in the problem, and everything else you need is given. And it kind of in parentheses, or a corollary of that is that if there are other unknown numbers that you just don't have, if you want to sort of define the system in a way so that you don't need those numbers. I'll give you a hint, or give you an example of that. If I don't know, two objects collide, and nothing else acts on the two. So the only thing in the problem are these two objects colliding, and they stick together and they move on. If you aren't given information about the forces, let's say you're trying to find the final velocity after they stick together, something like that. That's a typical problem. And you don't have any information about the forces acting between them, then you want to define the system in such a way that you never need to know the forces in between them. How could you do that? Well, if you make both objects be the system, the totality of them be the system, and there's nothing else acting on them from the outside, then there is no impulse, because the impulse only cares about forces from the outside on the system. So if I make the system be the pair of them, then you never actually need to know that force. And so there's sort of that's a strategy you can take to you're kind of shuffling things so that only the stuff you either want to find or already know appear in the problem, and the stuff you don't know doesn't appear. And then if a problem has many different parts, then you may redefine the system and reanalyze the system, or reanalyze the scenario each time, making it so that only the thing you want to find is is in the problem, and stuff that you don't know never appears. There's a little bit of that's actually the hardest part. The actual math in this stuff is usually quite easy. It's the hardest part is defining your system so that the stuff you know is enough to answer the question you're trying to answer. So, all right. All right, so after you identify the system, you write down the impulse momentum theorem. Usually it's this one, but sometimes it's the first one here. But you write down this here, and you identify either what you want to find or stuff that you have numbers for. You know, set things to 0, or if you have velocities, put them in. If you have a mass or something, put it in, whatever. Identify all the things you know, and then if you've done it right, you'll be left with just one thing to find. You just do algebra. So that's kind of our process of using the impulse and momentum theorem to solve problems. Figure out what you're trying to find, what quantity, define the system, and that's where the brain power, or that's where you have to kind of think it through. If you kind of slice it in different ways, it can either be trivial or impossible. So like I said here, in the car and person and cow problem, maybe you want to just focus on the person as the system, or maybe you want just the car as a system, or maybe you want the person and the car as a system, or maybe you want the cow as a system, or maybe you want everything as a system. Depending upon what the question asks you to find will determine how you should regroup things. Okay, that's the hardest part, I'll be honest, in the whole thing. And after that, you just write down this equation. And I will tell you, I write this equation, just like this every time. I start my analysis then, my math part of my analysis, with some statement that I know is guaranteed to be true. So I start with this. And then I just start plugging in all the numbers I have, and I find for the thing that I don't know. Okay, so that's kind of my general strategy for using impulse and momentum theorem. Are there questions on that? We're going to do some examples here, but is everyone clear on what the definition of momentum is? Yeah, mass times velocity. It's not complicated. It really isn't that hard. Impulse, it's a little trickier. We don't use that term as much in everyday language. It is the average force on the system times the time over which it is applied. And to come up with a number for this, or an answer for a quantity, you have to define the system first. In the problem in Sapling, there's usually an obvious way to do it. But that's usually what takes the most thought, is defining the system. Let's do some examples. Okay. So I took this off of, this is one of the Sapling questions. I don't remember which number. It's, these are my numbers. Your numbers would vary, but, oh, hold on, I need my calculator. Awesome. Okay, so what I want to do here is kind of go through, and I will kind of lay a strategy. And then what I think I'm going to do is break you into groups of 2 or 3 and give you guys 5 or 10 minutes. Maybe we'll say 5 because it always creeps out to 10, to work in a group to implement the strategy to get an answer. Okay, so that'll be the plan. But since I will want everyone for right now to use these numbers, you might want to take a snapshot on your screen or something, just so you have the numbers, so you have the problem right there, just so we all know what to do. I'll go ahead and read it here. So there's an open train car with a mass of 2010 kilograms, and it coasts along, so just, under its own momentum, just kind of carrying forward. There's no friction or anything, at a speed of 2.67 meters per second. The car, so we have a velocity of the train at the start. The car passes under a loading chute. Do you guys know what that looks like? I grew up right next to a train track, like a block away. So for me, I know what that looks like. So the idea is, you've got a train car. Let me draw a picture here. So there's a train car. It's on the tracks. And we're going to say at the start, there's a velocity of 2.67 meters per second. And then there is a chute over the top, which kind of is like a crane arm that will basically hang over the top and just dump stuff down. And so as the train travels underneath, okay, what's going to happen is that its mass is going to increase, right? Because there's going to be stuff loading from the top. So it's going to have some mass at the start. Stuff is going to fall into it. So there's going to be a new mass after the fact. All right. And all right. And then, and we are told that they don't just tell me how much grain falls in. I know though that they tell me that it falls at a rate of 447 kilograms per second over 3.43 seconds. So I know that the mass of grain, or whatever the stuff is, well, that's going to be the rate that it's added times the time. Oh. Times 3.43 seconds. Sorry, it looks terrible. Okay, so that's going to give me the mass of grain that's been added. All right. And then what they want me to find is the final velocity. That's what I want to find. And I'm going to go and say the mass of the car is 2010 kilograms. Okay, so I sort of have before and after. Now, I'll go ahead and give you a hint. Nothing depends on vertical direction. So don't worry about the, there's gravity, and then there'd also be normal forces in the vertical direction, but those are always just going to add up to zero because this thing isn't like tunneling. It's not going to, hopefully it doesn't cause the ground underneath to crater and cave in. So if that's right, then all of the stuff in the y direction just cancel out. And so the net impulse, the net force would be zero in the y direction, which means the net impulse would be zero in the y direction, which means the momentum doesn't change in the y direction. So nothing changes in the y direction. Okay, so you don't have to worry about that. Only focus on the horizontal direction. Okay. Let's do the first one here. I'm going to kind of lay out my idea on a plan, and then I want you guys to work through it in teams. The next one, I'll have you guys do more of the planning part of it. Okay. So for this one, as I look at it, well, let's kind of go through, kind of shrink it down a little bit. When I zoom in and zoom out, does it do the same for you guys? Yeah, okay. I never quite know how things transfer. Okay, so let's go through the steps. Do it just a little bit smaller so I can write them down. Step one, okay, identify the quantity you want to determine from the problem. So go through it. Well, I already kind of boxed it in. We want V final. Okay. Awesome. So we need, so then step 2, we want to define the system and do it in such a way that the only unknown is has to do with the thing I'm trying to find. So the final velocity, let's think about that. That final velocity, that number that I'm trying to find, would be the final velocity of the train, right? But it's also the final velocity of the grain or the stuff that falls, because they land and they kind of stick together, right? So that final velocity is this is the final velocity of both car and the grain. What do I not know anything about? Well, I don't know anything about how the grain actually collides with the car and bounces around, and I don't know any of those details. Okay, so I want to define my system to be in such a way that those forces are all inside the system, not kind of along the boundary of the system. So what I'm really getting at is, if I don't know anything about exactly the details of how the grain collides with the train car, then I'm going to make the system equal the car and grain together. And so that we never need to know about forces between them. Okay, so the idea is here, you have your system here. So we're going to have the change in momentum of my system, and then the forces from the environment give rise to an impulse. But if I so it's only the forces from the environment, the surroundings, that give rise to the impulse. If I put the grain and the car both in the system, well, the forces between them don't cross the boundary of the system, so they don't give rise to an impulse. That's kind of the trick to the whole thing. All right. So there you go. So I have that. To find my system, I write down the impulse and momentum theorem. And again, so okay, I do that. 3. I write down the impulse momentum theorem. So I'm going to say the change in momentum equals the impulse okay. And remember, I can write it like this. This was only adapted for just a system with one object, but now my system has 2 objects, so I'm using the top one, and it'd be the total momentum. Okay, so you have to use the total momentum for the system, and all right, and then it's this next thing is identify, evaluate all things you already know. Okay, so 4. Well, I define the system so that the impulse from the impulse from the outside world acting on the grain and the car or the train in total is 0. So I would have 0 equals the change in the momentum of the system. All right. That's my plan. So this is my key equation. So what I need to do is, or I guess, so I need to. So what I'm going to have you guys do, evaluate the change in momentum of the system. So you need to find the momentum of the system before. So, and write down a formula for the momentum of the system after. That'll be any, right? That'll be a symbol, a formula. And then use delta P equals 0 to find the final velocity. Okay, so that's the plan. Before I break you up into groups, does everyone have the numbers that they need or have a snapshot so that you have it? Because once I put you in groups, you won't be able to see that. You guys, there's a whiteboard feature and you can annotate. So what I want you to do in each group is I want you to use the whiteboard feature to draw and annotate. And I know it's clunky using your finger and a trackpad, but try to do the best you can. Don't worry if it's not good. I'll just make fun of you. So no, just Charles, only Charles. Okay, so I'm going to break you into groups, and then I'll give you guys 5 minutes to work on it. Breakout rooms. Come on. So we have 9, 4. Okay, everyone should be moved to a breakout room. How's it going?
Hello.
All right. Do you guys see how to use the whiteboard feature? If you go to share screen at the bottom,
Share screen.
there should be a whiteboard option.
Where's that again? You said share screen.
Try it again. Try share screen. Can you?
Now I can.
Now I had to check something. It's my fault. Okay. So Josh, why don't you, Josh, why don't you use your whiteboard, and then Brielle, you can do annotate at the top, and you can also draw there.
Wait, was I supposed to click share screen too? Because it doesn't let me.
I think if he's doing it, then you won't be able to, and you can go back and forth. But I think only.
Okay.
Okay, so Josh, you can draw. Brielle, try use annotate and see if you can draw on his screen.
I don't have an annotate thing.
You don't have an annotate thing. Well, Josh, if you go to share screen, can you, go up to view options at the top.
Okay.
And at the bottom, there's an annotate option there.
Oh, okay. I have it now.
Okay, so see if you make sure you can do that.
Okay.
All right. If that works, then I will go to the other groups and make sure they're going. Awesome. Okay, and then Brielle, I think you have to remove your, to undo it, you have to, yeah. All right, awesome. Okay, do you guys think you know how to start the problem?
I think so.
Yes.
All right, give it a try and I'll be back around.
Okay.
I think you're muted.
Ha. Did you figure out, so this is Taylor's screen, but Jessica, you can also write on it. You can annotate. Do you know how to do that?
No.
Go up to view options at the top and there's an annotate link and then you can write.
Okay.
And then I think Taylor won't have control of the things you write. So if you want to make them go away, you have to.
Okay.
Yeah. All right. Okay. So tell me, what's your plan here? What are you trying to do?
We don't really know yet.
Okay. So
this is the only thing I remember from my high school physics. I don't know if we could use that here.
okay. So remember, so what do we get? Yeah, sort of. Very close to this. Let me see if I can annotate. So what I would say is we're going to use the following. We're going to say, first of all, what's the momentum of, what's your system? It's going to be the car or the train plus the grain, right? Okay. What is the, so the momentum of the system would be the mass of the car times the velocity of the car plus the mass of the grain times the velocity of the grain. Okay, is that okay? That's using the, that's all right. That's for the total momentum. Jessica, is that okay?
Yeah.
Okay, now we only care about X direction. So don't worry about the Y direction. Okay, so now our impulse momentum theorem says that the change in momentum of the system is 0, which means the momentum of the system before equals the momentum of the system after. So just apply this formula before and apply this formula after and just set them equal to each other. And you can solve for the final velocity using that. Okay, I'm going to leave you guys, work on that, think about it, and I'll kind of pull everyone back together. Okay? Oh, sorry. Well, canceled the meeting. Hello?
Hi.
Hey, so were you guys able to use the whiteboard space? Did you see how to do that?
I don't know.
Awesome. Let's figure that out because it'll be useful. If you click on share screen, just one of you, it doesn't matter. There's a whiteboard option. Do you see that? Or no?
Yeah, I see it.
Okay, so if you click on that, awesome. So right now, so I can see Rachel's screen, and then so you can draw with your finger. It's a little clunky, but you can do that. And then, Madeline, if you go up to the top, do you see view options?
Yes.
Okay, if you click on that, there's an annotate option.
Okay.
So then you can write also.
Okay.
The only thing is you can't control each other write. So if you need something to go away, that person has to remove it.
Okay.
All right, so let's talk about the problem. Where to start?
We started with we multiplied the 3.43 times the 447 to get the additional mass at the end.
Okay.
And then we did 210 times the 2.61, which gave us 5,246.1. And then after that, we, where is it? Oh yeah, that was we said that was the before momentum, was the 4,246.1.
So let's write it down here.
Okay.
So okay, first of all, let's go through the process. The first thing was to define the system. So what did we say to make, what did I suggest to make the system? Car and the grain. Okay. So now this is a system with two things. What's the formula for momentum for a collection of things? Do you remember that, Rachel?
Isn't it like the sum of
Yep.
mass and the velocity?
Yeah. So I'm going to say that the formula for the total momentum, or for the system momentum, is mass of car times velocity of car plus mass of grain times the velocity of grain. Is that okay? And remember, we're only worried, we focus on the X direction. Okay, so don't worry about the vertical stuff, just worry about side to side. So in particular, at the very beginning, before the grain falls on there, what is the velocity of the grain in the X direction? Think about it.
2.67.
No. Which way is the grain moving? What does it do? It just falls down, right?
Yeah.
So that means at the beginning, there's actually no momentum in the X direction because it only moves up and down. And we're only focusing on the X direction. So at the beginning, the velocity of the grain will just be 0. Okay. So, all right. So at the beginning, I know the mass of the car was 2010 kilograms. The velocity, so at the beginning, velocity of the car, they gave me a number. I don't remember what it was. Do you have that?
2.61.
And I'd say the mass of the grain, what was that number? You had to multiply those two numbers.
1,533.
Sorry, say it again. Sorry.
1,533.21.
Okay. That's the mass of the grain. And what's the initial velocity of the grain?
0.
0. In the X direction. Everything's in the X direction. Okay. So you've got these numbers. You could figure out the momentum before, for example. All right. Now, what I then suggested was to use the impulse momentum theorem. So then say delta P for the system equaled the impulse on the system, but that was 0 because there's no outside. It's not like there was wind blowing from the side or something else pushing it. There was no sideways force on the whole system. And if you think about it, that means that the momentum of the system before equals the momentum of the system after. Madeline, do you see where I'm getting that?
I'm kind of confused a little.
Okay. So the impulse momentum theorem said that delta P equals J.
Mm-hmm.
That's always true no matter what. So I always start with that because then I know I'm not making a mistake.
Okay.
And then because we put everything, all told, everything in the system, there's nothing outside the system that does anything. So the impulse has to be 0.
Okay. But why would we equal like the before and like the before momentum to the after momentum if we're
Well-
like adding more mass and stuff to it?
Well, so what's going to compensate is okay, the momentum. So what this says is the change in momentum is 0. So that means the initial equals the final, which is what I wrote here.
Mm-hmm.
And then the idea is if the momentum can't change, you're right, the mass grows. So to compensate, the velocities will have to shrink.
Okay. That makes sense.
That's how it's going to work out. All right. So what I want you to do is just go back and you basically use this formula for the momentum of the system, apply it before, and then apply it afterwards, and use this equation to figure out the final velocity.
Okay.
All right. Rachel, is that okay?
Mhm.
All right. I'm going to leave you guys. Try to figure it out.
Okay.
You're on mute.
That didn't sound like a train going down a track problem. I'm hearing laughing.
Well,
right.
you see, we're really good, so we got done a very long time ago.
Good. All right. First off, let's figure out the whiteboard space thing.
Yeah, I don't know how to do that.
Right. Chloe, click on share screen.
I'm like on a weird device using Zoom, which is why I don't have
Okay.
a camera, so I don't have any of the normal like
So
access
you don't do that.
things.
Charles, you click on share screen. Click on screen.
Okay. It gives me an option.
Okay. Click on it for whiteboard.
It doesn't say whiteboard. It says desktop or application.
Wait, so you have, when you see share screen and it doesn't have a whiteboard option?
Nope.
Desktop.
May I ask what type of laptop you have?
Oh, I have a Mac, but other people are using Windows, so it's.
Oh.
It,
Well,
it's-
I don't have that. I have a Chromebook.
Oh. Okay, so when you click on share screen, what does it say?
It says, do you want to share? And then there's 2 buttons. The one on the left says to share desktop. The one on the right is to share an application, which would be like multiple slides or apps on the computer.
That's going to be the problem. All right, so when you do this, there's a Google like note-taking app. I don't know what it's called, like where you can draw like Google Docs kind of thing.
Okay.
So you would want to pull that up because then I bet you could share that screen.
Okay.
All right. So what I'm going to do, tell you what, I'm going to pull everybody back together and we'll solve, but I didn't realize Google Chromebooks struggled with this. So that's how you would want to do it though. You'd want to use the Google suite of apps. I think in one of those, it might even be just Google Docs, but there's a way to draw in one of those programs. That's the one you'd want to use.
Okay.
And you would draw with your finger and right there. And Chloe, I'm going to share mine. Let's see what you have options for. So can you guys see a white space here?
Yeah.
Okay.
Yep.
Now, if you go up to options at the top, do you have that as an option? Is there a link or a button for options?
I don't have options.
Chloe.
Next time I'll be back on my computer, so this won't be a problem. This is just
Yeah.
temporary.
Okay. There should be an option for, actually, let's try for Charles. Do you have options at the top?
At the top?
Yeah, I don't know where. For me, it was like top center, but I don't know what you'll see.
I have an options drop down tab.
Okay, click on that. Is there an option to annotate?
Nope.
Oh, wait. I can draw.
That's awesome. All right. So Chloe can draw. Look for options. Charles, I bet there's a way for you to do it at the top.
There was just a like pen emoticon at the bottom of my screen that I clicked on.
Okay, try that. Nothing? Charles?
Oh no. Chromebooks are they're limited when it comes to this type of Zoom stuff.
Okay, so when you're doing it, I think what you want to do is go through the Google Chrome apps, and one of them is like a drawing program. And so if you use that, then in the group, then other people could annotate on top of yours, I think. But okay, so that'll be the strategy. All right. I'm gonna pull everybody back together, and we'll work this problem out as a group. Okay.
Okay.
Stop share now. Leave breakout room. Close all rooms. Okay. Yeah, I think we have almost everyone back. Maybe we lost somebody. All right, maybe they'll come back. Maybe. All right. So let's. Now I don't know if everybody quite got through this one, so let's kind of run through it as fast as I can here. Where's my toolbar? All right. I know what I want to do. Sorry, I'm struggling to find as I go from place to place, I lose tools. There we go. Okay, so let's go through this one. And the idea is going to be that the momentum of the system is going to be, because the system is both the grain and the train, it's going to be the mass of the grain times the velocity of the grain plus the mass of the car times the velocity of the car. And my key equation says that the change in momentum of the system is 0. So that means that the momentum before the collision is the same as the momentum after the collision, because it's not changing. So I would say I want to write down the mass of the system before equals the mass of the system. Oh, sorry. Equals the momentum of the system after. So what we're going to do, or what I need to do, is apply this formula, mass times velocity plus mass times velocity before the collision, and then write it down after the collision and rearrange it and solve for the final velocity. Before I do that, are there any questions about where I'm getting that? So I'm really saying the change in momentum of this total system has to be 0. So then I just am going to evaluate the total momentum before and then write down a formula for it afterwards and get my answer. Okay, so when I do that, I'm going to need someone who's got the numbers here. So I'm going to erase things to kind of, I don't know. I know what I'm going to do. I'm going to move the next question down to give me some room. Okay. So before, I have the mass of the grain. What's the mass of the grain? That was, somebody told me it was like 1,000. What was it? What is, can somebody call out the mass of the grain?
2010.
Oh, that's the car.
Oh, that's the car. Sorry.
Well, we can
447, I think, kilograms a second.
1,000. What was it? Can you say it again?
447.
447. Oh, I
And
have to
then-
multiply by the time. Yep.
Yeah, and then times it by the 3.43.
Yeah. So what does that give you?
Then you get 1,533.21.
Sorry, that's the mass of the grain, and then I need to multiply by the velocity of the grain. Remember, it's falling straight down, but we only care about the x direction. So what is the initial velocity of the grain in the x direction? Well, if it's falling down, then the velocity in the x direction is 0. So this would be the mass of grain, the velocity of grain before. So that's the momentum coming from the grain in the x direction. And then I have to do the same for the car. Its mass was 2010 kilograms, and its velocity was 2 point, what's that number? It's up here. 2.61. So this would be mass of the car times the velocity of the car, all evaluated before the collision. So if I clear that, 2010 times 2.61, that gives me the momentum before is 5,246.1 kilogram meters per second. Can you give me a thumbs up if you see where I'm getting these numbers, like why I'm writing this down? Okay. Josh, you okay? Yeah, Brielle? All right. So that's the momentum before. And then afterwards, I don't know the velocity after. That's the point of the problem. But the grain still has the same mass, and the car still has its same mass. So that's going to be 1533.2. But I do know they have the same final velocity, plus 2010 kilograms times the same V final. I can rearrange that to write that as 2010 plus 1533.2, 3,542.43.2. Times V final, because they have the same final velocity, so it factors out. And then my key equation says that the change in momentum is 0, which means the momentum before equals the momentum after. So that means this number equals this expression. So I have to set them equal. So I get 5,246.1 equals 3543.2 times the final velocity. And so what's happened is the mass has grown, and the velocity is going to compensate by decreasing. So if I rearrange that, I do 5,246.1 divided by the answer, and I'm getting 1.48 meters per second. I divide both sides by the mass, the total mass. Okay. Can you give me a thumbs up if you feel like you understood that? Yes, yes, yes. All right. Are there any questions on that? The logic of how I did that? Okay. All right, let's do the next one. And probably run a little, this one I will try to kind of guide you through a little bit closer. So this one, uh-oh. All right, we're going to do this one. We probably won't get to the next one, the broccoli one. Sorry. All right. So in this one, let's move that up. We're going to focus on the astronaut one. It's a very easy problem, but it's weird, and so people get confused by it. So here's the deal. There's an astronaut. He's got tools with him, and he's floating through space. So actually, hold on. There's a spaceship. I don't know. My spaceship looks like an airplane. Anyways, and then there's an astronaut floating in space with a toolbox. Okay, or tool, or what is it? Yeah, bag of tools. Oh, sorry. It should be a bag. And so the problem is that the astronaut and tool they've lost contact. They're drifting away. So they're drifting away. And the problem tells me that they are initially drifting away at 1.2 meters per second. So they're floating away from the spaceship. Uh-oh. And so they're going to go off into the darkness of space. So the astronaut has an idea. And basically, the astronaut is going to throw the tools forward. So the tools are going to have a really big velocity going forward. And then he wants to use the recoil to basically bring his final velocity to be 0. So ideally, he would actually have a negative velocity so he could go back to the spaceship. But the problem says, what is the minimum speed of the tools that will keep the astronaut from drifting away forever? So basically, we want the final velocity of the astronaut to be 0. Okay? So the idea is the astronaut's going to use the recoil to bring him or herself to a stop. Okay, that's the idea. So we're going to go through the same process and use impulse and momentum to solve this problem. We don't know anything about the details of how the astronaut pushes on the tools. You know, is it a one quick push or is it a long, steady push? We don't know. So because we don't know anything about the forces between the astronaut and the tools. We need to define the system so that you never need to know those numbers. So that means you want to bury those interactions between the astronaut and the tools, put that inside the system. So that's got to all be internal stuff so that it never contributes to the impulse. Any guess as to how we would want to define the system then, so that you never need to know details of what goes on between the tool and the astronaut? No one wants to guess. All right. So what we want to do, though, it's kind of like the last problem. We could, rather than making the system be the astronaut by itself or the tools by themselves, we make the system be everything all told. So make the system is the astronaut, so the person, and tools. So we don't need to know about the forces between them. Okay. And all right, so that means also then, just because it's in space, there's no other force acting on it. The ship is far away, it's not pushing on it. So that means there are no outside forces. That also means no impulse. Right? If there are no outside forces acting on the combined system, then there's no impulse. All right. So we write down, the next thing we want to do is write down our impulse momentum theorem. Delta P equals J for the total system. But the impulse is 0. So that's just going to mean that the change in momentum is 0, which means the momentum before equals the momentum after. It's actually very much just like the last problem we did. All that you have to do is write down the formula for the momentum of the system. So that's going to be the mass of the person times the velocity of the person plus the mass of the tools times the velocity of the tools. And then apply this formula before and after. Before, so, okay, so I'm going to do the before. So we're here on the, and the, let's see, the tools have a mass of 10 kilograms. The person has a mass of 124 kilograms. And the velocity is 1.2. So I'm going to say 124 kilograms. Oh, is that right? Sorry. Yes. That's the mass of the person. The velocity of the person is 1.2 meters per second plus the mass of the tools times the velocity of the tools before, well, they were moving with the person, so it's 1.2 meters per second. And I get 124 times 1.2, and I get 160.8. And that'd be kilogram meter per second. That's the momentum before, what I have on the left. And I need to write down a formula for the momentum afterwards. So that would be mass of the person. And what's the final velocity of the person? Well, you throw the tools, you want the person to have come to a stop. So their velocity is going to be 0. And so I just have mass of the tool. So I have to add in the momentum of the tools. So that'd be 10 kilograms times V final for the tools. And then I have to set these equal to each other. So if I set these equal, I find 160.8 kilogram meters per second equals, the person has no momentum, so that is 0. You only have the tool's momentum, 10 kilograms times the velocity final of the tools. And therefore the final velocity of the tools would equal 16.08 meters per second. Okay, I know I'm running over time, but does, I guess, I'll go ahead and you can write that down. I will post these, I'll upload these in a PDF file too, so you can see exactly how I did things that way. Can you see how this problem is very similar to the last problem? I know the story is different, but the actual steps are very similar. And that's always true. All of these momentum problems, ultimately, the words change, but it's going to be this game. You define the system in some way so that what you don't know isn't important. And then once you do that, the rest of it just, you really, if you've done it right, you almost always just have one unknown figured out. All right. Who would want me to do the other problem, the last one? It was the one where there's a restaurant and two people throw their food and the food collides and then it sticks together in some horrible mismatch. And you're supposed to find the final velocity, I think, of the food that's left. Should we do that one? I guess I'll tell you what, if you need to go for another class or something, you can go. I will work it out, and if you have to go, it'll be uploaded. I'm also going to put this on YouTube so you can watch the rest then. Okay, so I think we'll do that. So if you have to go, don't worry, I won't be offended. I'll do that. Just go if you have to. I don't know, maybe just do it here, I guess. All right. Of this problem. Okay, so there is a pizza sliding on a counter with some, it goes from the left to the right. So we'll call that the positive X direction at some velocity. And the chef throws a veggie burger. Everyone's vegetarian here. It's good. All right. Some other mass. And to the left. So I'm going to say that the pizza has a positive velocity. Sorry, the videos are flipped. The pizza has a positive velocity. The sandwich has a negative velocity. And they collide, and there's no friction, so don't worry about that. And they merge into a single pile of food. Oh, anyways, the problem got cut off. We're supposed to find the final velocity of this big pile of food. That's the goal. So we want, I didn't snip that out. That's what we want. Okay. Again, so we want the final velocity. What do I not have any information about? These things collide and stick. It's really gross and terrible and complicated. I have no information about what? Think about the last two examples. What we didn't have information about then. And this one's kind of the same.
When the forces combine and like
Yeah,
the particles react against each other.
yeah, I don't know anything about that. And so that means I kind of want to hide that problem by putting that inside the system. Make the things you don't know irrelevant. So if I make the system be both pieces of food together, then that force between them just doesn't matter. Okay, so that's what we're going to do. So I make my system be both foods. So the impulse will be 0. That's the goal. I just kind of, that way I don't need to know it. If, for example, I made the food, if I made the system be just the pizza, then I would have to, then the hamburger is going to push on it. So if the system was just the pizza, there would be some outside impulse acting on it. And I have no way of coming up with those numbers. And so I would be kind of stuck. So by doing it this way, the things I don't know aren't a problem. All right, so then the impulse is 0. I'm going to say delta P for the system is 0. So I'm going to say the momentum before is the momentum after. So the momentum before is after, and it's just really just like the other problems. I'm going to say the momentum formula for my system is going to be the momentum of the pizza. Oh, sorry. I'll just write is the mass of the pizza times the velocity of the pizza plus the mass of the veggie burger times the velocity of the veggie burger. And I'm just going to apply this before and apply it afterwards and set them equal to each other. So before the collision, I would say I have the mass of the pizza, which is 0.207 kilograms times the velocity of the pizza, which is positive 1.73 meters per second, plus the momentum of the veggie burger, which that is crazy. The veggie burger has a bigger mass than the pizza. They must be thinking of a slice of pizza. Anyways, that would be 0.325 kilograms. I've converted from grams to kilograms. It won't really matter for this problem as long as you're consistent, but it's probably just a good habit to get into. So I usually do it. And then I have the velocity of the sandwich, but the sandwich was going in the opposite direction. So I'm going to say that's negative 2.43 meters per second. This minus sign. Right? These are vectors. So that means they have all the vector things, minus signs. And if we were in 2D, you would have X and Y direction. You'd have to do it separately in components and work it out that way. All right. So that's the momentum before. I can just type it all in. 0.2071 times 1.73 plus 0.325 times negative 2.43. And I get a total momentum of negative 0.431. And that'd be kilogram meter per or meter second. Oh, I've got to represent kilogram times a meter over a second. That's the momentum before. I need to write down a formula for the momentum after. Well, I don't know the final velocity, but I have their masses, so I can say that's going to be for the pizza 0.2071 times v final, which I don't know, but they have the same final velocity, so that's all I need. Plus 0.325 for the sandwich, for the veggie burger, times again the final velocity. And I can add those up. So that's going to be 0.325 plus 0.2071. Oh no, there's no one there. That should be kilograms. Sorry. So that's going to give me that this equals 0.532 kilograms times V final. 532 kilograms times V final. And now going back to my key equation, that the momentum before is the momentum afterwards. So that means that this is the momentum before equals this momentum afterwards. And I get negative 0.431 kilogram meter per second equals 0.532 kilogram times V final. I want to find the final velocity, so I just divide. I get V final equals I hit the wrong button. There we go. I'm getting negative 0.810 meters per second. Okay. You see, this problem is really the same as the other two. I mean, the basic idea is the same. Once you define the system in a useful way, it kind of unravels in the same fashion. All right. I will upload these notes to Blackboard so you can see them. Do you guys have any questions on that? Chloe, I can't see you. Are you doing okay?
Yeah, I get this one.
Okay. On Tuesday, I worked an example where there was one system and we broke it up. We did it twice. And one of the ways you did it, so we did it so the impulse was 0, and we did that to find a final velocity. And then afterwards, we regrouped it and used that final velocity that we had already determined to find the average force between the two objects. So there was an impulse. So there are some sampling questions like that. You might want to look at the notes or the video from Tuesday's thing. It'll help you figure out how to do that. It's really not very hard. It's just a slight little wrinkle. Okay. All right. So that's what I wanted to do for today. I will let you guys go then, and I'll post this stuff. Okay. All right. Have a good weekend. And next week, we'll talk about energy ideas. Also, there are some YouTube videos that I recorded last semester, both on momentum and then also for energy for next week. So you can watch those to help you. All right. See you guys.